We're back on the subject of the coronavirus pandemic again, and unfortunately we have a graph here of the total worldwide deaths that have been attributed to the virus. At first the graph doesn't look too concerning. The slope is obviously upwards, but it's not rising at any kind of dramatic rate. However, that's before you notice that the scale on the y-axis isn't a normal linear scale. 10, 100, 1,000, 10,000, 100,000. It's not going up by a set amount. In fact, it's going up by 10 times every single step. The graph on a linear scale actually looks like this. It's the same data, but now the scale is going up in steps of 10,000. So this is a normal linear scale. We have the same gap each time. This is called a logarithmic scale, where each step on the graph actually represents multiplying by 10 rather than adding on a certain amount. Now, the reason they've done this is not to be misleading, but there's lots of useful things you can do if you have a fairly linear looking graph as opposed to an exponential graph like this. You can find a y equals mx plus c regression line, you can find the gradient, you can find the y-intercept, you can talk about correlations, you can use Pearson's moment correlation coefficient. All that stuff is possible with this graph, but not with this graph. So there's good reasons for doing this. There's another very common logarithmic scale that you will have heard of, the Richter scale for measuring earthquakes. I think it's a good example of how logarithmic scales actually work. In 2003, there was a magnitude 8 earthquake in Japan. And pretty serious, but there were 0 deaths. The next year, there was the famous Boxing Day 2004 tsunami in Indonesia. That was an earthquake of magnitude 9, and that resulted in 250,000 deaths. There's reasons for this other than the magnitude of the earthquake, where it hit, the time of year, the country it hit. However, it can't be ignored that one of the big reasons why this was so much more devastating is it was a lot stronger. A magnitude 9 earthquake is not just a little bit stronger than a magnitude 8 earthquake. It's 10 times bigger. Because these numbers on a logarithmic scale are powers of 10. So when you go from 8 to 9, it means you've multiplied by 10 one more time. If you were going to go from a magnitude 5 earthquake up to a magnitude 7 earthquake, that's 2 extra powers of 10. That means you would have multiplied by 100. A magnitude 7 earthquake is 100 times bigger than a magnitude 5. So these get pretty big pretty quickly. The maths involved in producing a graph like this uses logarithms, which we've seen before. We're going to quickly revise that now by going through a few examples. You can skip this if you are already confident you know how logs work from the work we did in September, but I do recommend looking at the examples just to refresh your memory. So logarithms are basically a way of rewriting this kind of relationship. So 3 to the power of 4 is 81, 2 to the power of 5 is 32, 10 to the power of 2 is 100. We can use logs to twist this around. So this relationship here would be written this way with logs. There's the log. The base number 3 is the base of the log, and that goes down here. The output of this calculation goes inside the log there, and what this is equal to is the power. So you can think of it as saying, what power of base 3 would give me 81? 4. Okay, let's do it with this one here. We're asking what power of base 2 would give us 32, and the answer is 5. This one here, what power of base 10 would give us 100? It'll be 2. So just test yourself quickly. If I write down, let's say, log 5, and then I put 125 in there, I hope you're thinking that 3 is going to be the answer, because 5 to the power of 3 gives you the answer of 125. There's a couple of little bits of notation we need to be aware of. I've written down log base 10 here, but actually base 10 is such a common log that we have a shorthand for it. So log base 10 is just written as log. And on the calculator, there's a button that just says log. That means log base 10. So whenever you see log, it means base 10. Another one is E. So when you see ln, this means log base E. E is a very, very common number when it comes to exponential graphs and functions, so it has its own notation. It's called the natural logarithm. And it's written ln. And again, on the calculator, it's got its own button. And on this course, you're only going to be using these two logs. You don't have to worry about any of the other ones. They do exist, but these two are the most common, and you're going to see those two predominantly. So if we look at some of the things you can do with logs, let's just say, in fact, if you look at example 15 yourself, hopefully it makes sense what I've just said and where those come from. But what we're going to look at in more detail is some of the log laws. So these are here. Again, you've seen this before. Just remind yourself what they are. Look through the example there. I will just show a couple of them, like from first principles. So if we think about powers of 10, what is 100 multiplied by 1000? Well, of course, it is 100,000. This could be written as 10 squared multiplied by 10 cubed. And of course, if you have the same base, you add the powers. So you get that. If we just separately now think of what all of these would be using the log relationship. So log of 100, remember it's log base 10, but you don't write the 10 in there. That's 2. Log 1000 is 3. Remember these values here, these are just the powers that are coming out. And log of 100,000 is 5. Okay, so when you multiply these two base numbers here, these two original numbers, 100 and the 1000, and you think about them as powers of 10, you add the powers. So if I was going to try and make a similar equation using the logs, so let's say log of 100, and then we've got log of 1000, and that's supposed to equal log of 100,000. What operation needs to go in here? Well, this is 2, this is 3, and this is 5. So clearly we have to add these two to make that. And that's because logs represent powers. Therefore, the rules for them are the exact opposite of the rules for base numbers and powers up here. So when you have the same base and you're multiplying those, you add the powers. Here, when you have the same base and you're adding the logs, you multiply the numbers inside here. So the general rule here is if you have log of x plus log of y, make sure that's a clear G there, that would be the same as log xy. So same base, when they're being added, you can multiply the numbers in there. And it gives you this. Division is the same. If you're going to subtract these, then you would divide those two there. There's one more rule that comes up quite often as well, which is what happens when you have logs that have a power themselves. Well, going back to this one, log 100, obviously that is going to be 2. But you can think about this as log of 10 squared, which is 100. Well, we know the value of this is meant to be 2. If I just ignore the power there temporarily, what is the value of log 10? Well, it's saying what power of 10 gives me 10? Well, the answer to that is 1. But 1 squared isn't 2, and this needs to be 2. So it's telling us that actually what we need to do here is we need to take this log 10, which is 1, and we need to multiply it by 2 to get the same value as that. So we can say this is true. And that comes from the rule that if you have something like a power like this, and a bracket, and then the whole thing is to a power, we know that we actually multiply those there. So it's the inverse of that rule there. In other words, if you have log, let's say we're going to put x to the power of b, we can rewrite that as b up the front log x. So the power goes from there to the front, and it's that. Okay, so those are the rules you need to know. Again, I'd look through example 16 and see if you can work out those and make sure you can see where all those have come from. From there, there's some questions to practice. Some of these are pretty tricky. I think I will show an example of a couple of these. Maybe the first one here, I think. No, in fact, those ones I think are okay. Let's just skip over to these ones here. So the next one, 7k, there's a couple ones here that are actually quite difficult, I think. There's a little box of information in the graph up here. Just want you to read through that and see if you can see where the graph comes from. I recommend maybe going on to Desmos and plotting y equals log x, so you can see what that looks like, and then hopefully you can see where these facts come from. I'll let you look at that yourself. Let's go through a couple of examples of how these questions here work. So if we pick out, say, 1bi, this one here, we're trying to solve a logarithmic equation like this. So we've got e to the 3e to the x minus 1 equals 14. So we're trying to solve this. That means we're trying to work out what x is. And in this question, we have to give our answer as a logarithm. So you do this by trying to isolate the x as much as possible, like in any equation. So if we add 1 to both sides, we're going to get this. Divide by 3, we're going to get this. And then if we're going to try and turn this into a log situation, then that means we have to rewrite this, do the switching process I showed at the start, now using e. That means it's going to become base e, so we use natural logarithm, that just means base e. 5 is going to go in there because that's the output, and therefore it's asking what power of e gives you 5. Well, in this case, that's x. So the answer we've got actually is this. You can go on the GDC and actually type that in, and it will give you the exact value. But you don't have to do that in this question. Might be interesting to see though. So we just quickly look at that. Natural log of 5, and it turns out to be 1.609, so on and so on. If you take that number using the answer key, and if you get e, and you make e to the power of that value, the whole point of this system is that we've just worked out what power of e makes 5, and there you go. We look at also maybe question 3b, that might be quite a good one to see. So in this one, we are doing some log simplification. It looks pretty daunting initially, but it's not quite as complicated in practice as it seems. So let's try to simplify this as much as possible. We have to realize that if we've got powers being subtracted, that means that the original numbers would have been divided. So you can write this like this: e ln x divided by e ln y. And just like if it was something like, I don't know, 10 to the power of 5 minus 3, you'd get to that situation by doing something like 10 5 over 10 3. So when you're dividing, you subtract the power. So this is a reverse of that. Now in this situation, you have to recognize that these two are inverses of each other, which is something that was said in the notes that I skipped over earlier. So this one's saying, if we make e to the power of this, what's that going to be? Well, this whole thing, ln x, that is saying, what number do you raise e by? What power of e do you want in order to get x? But that is the power of e here. So whatever that is, the value of that is going to be x. And the value of this one, in the same way, is going to be y. Maybe we take another example of how that works, make it a bit more obvious. If we say, okay, log base 10 of 1,000, well, the answer to that is 3. If I then take 10 and I raise that to this power, if I do log 1,000 there, the answer is going to be 1,000, because that is 3. Because it's asking what power of 10 do I need to get 1,000, and it's giving me that answer, and then I'm putting that answer in the power position, so therefore I'm going to go and get that. So that's your answer to those. And one more, I think, from that exercise might be useful. Question 5, where you have to do an inverse function. Just very briefly do the start of that question there. This works in the same way as any inverse function would work. In this case, we have a power to deal with, so a log is going to appear. Here's the function in its original form. So if we do an inverse function, it's always the same method. We're going to make that equal to y, rewrite the function there, rearrange it so that x is the subject. Well, we're going to add 3 to both sides. How do you stop x being up there in a power? Well, if you then rewrite it in terms of logs, then that will give you that. So we're saying, okay, what is the power? The base is 10, sorry, so we're going to say log, that's base 10, of y plus 3. And we're saying what power of 10 gives you this answer? Well, the original statement was saying that 10 to the power of x gives you that answer, so therefore this must be x. So it's quite a neat little trick. When you just do the log of both sides, it basically gets rid of the base number, brings the power down to the normal level, and puts the answer inside a log. This is a very useful thing to do, and this is actually where the graph comes from, which we'll come onto in a very short amount of time. The actual function, therefore, the inverse function, remember we don't use the y, we're going to say that that is equal to log x plus 3. And that's a graph that you can make. That's a better one there. Okay, so that's hopefully enough information to have a go at most of those questions. Just very briefly, we'll look at the last thing in this section, which is how the graphs themselves actually work. So the box at the top here is giving you an explanation of how that original graph, that virus graph I showed, how it was turned from an exponential graph into a linear graph. I'll just grab this again, actually. So that first graph, this one here with the exponential curve, this would have, most likely, because the deaths are multiplying every day, let's just take a random example. Let's say the function would be something like y equals 5, and then every day there was 10 times more deaths. Like, it's not really that bad in real life, but let's just use an example. You'd be doing times 10 every day. So then if you're going to the third day, you do times 10 twice, the fourth day times 10 3 times, and so on. So the variable would be this x. And you could do an x minus 1 there, depending on how you start at the end of term, but you generally have this kind of equation here. So this is going to be an exponential graph, because you're timesing by 10 another time every time you increase something on the x-axis. Now, if you take that and you do logs to it, you can make it into a nice y equals mx plus c sort of format. So I'll just take you through the general example of how that would work in this particular case. So if we do log of y there, and we're going to do log of this just whole thing here. Okay, so you just basically put both of these things into a log. Now, the left side is not going to be simplified at all, so I'm just going to write equals there for now. This side here, though, we know from the log rules that if we've got two things being multiplied here, we can actually write those as separate logs being added. And in this case, we can see as well that because we've got this power of x here, another of the log rules allows us to bring that to the front. And in this particular case, because we had a base 10 and we used a base 10 log, this log 10 is just going to be 1. So this whole thing simplifies down to essentially some function of y. This log 5 is probably quite a nasty number, but it is just going to be a constant. So it's essentially going to be a c. And then we've got our x with a gradient in front of it. Now the gradient in this case is going to be 1. That would be 1. But it might not be. It just happened to be that I was using base 10 and a 10. So you've essentially got a y equals mx plus c sort of format. You look at the note here, that's what's happened here. So it goes from y equals ax to the power of b. Using logs, it becomes this. I think it might be interesting for you to see if you can make this out of this in the same sort of process I used there for that example. With that, you can then answer the questions on the log graphs. Think again about what I was saying with the Richter scale. If you look at the exercise 7L, actually the very first question on here is asking a very similar question. This table of data has had the logs already taken, so they've already done the log process, and it's saying, well, how would you work out what the data was originally? So this one here, the b value is 3.2. Well, that means that was the power of 10. So it was 10 to the power of 3.2. The g value is 10 to the power of 6.6. Then it's saying, well, how many times bigger are those? So 6.6 isn't that much bigger than 3.2, but when you put them back into powers of 10, you'll see that actually they are quite a lot bigger. So have a go at that question. Send me any questions you're not sure about, but hopefully that does make some sense.